All right, this is Honors Algebra 2 Pre-Calculus. We're doing 4.3 in Pre-Calc. This is our third video in the section. We're doing an intro to right triangle word problems. So we can also solve for side lengths in a right triangle if we know one side and one of the oblique angles. We'll start by doing this with a few triangles with no words, and then we'll progress to some sweet word problem action. A few key terms before we hit the word problems. The angle of elevation is the angle from the horizontal looking upwards. So let's say that we're in the normal world, right? And I'm standing here teaching a class, la da 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 da, and you're sitting at a desk, da 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 da. That's you, right? Okay. So I'm higher up than you are because even though you're probably taller than I am, you're sitting in a chair and I'm standing up. That's my version of a chair. It's terrible. Okay. So we both have this horizontal line of sight, right? So like this, right? That's horizontal, right? And horizontal lines are parallel to other horizontal lines. So as I look down towards you and you look up towards me, right? This angle right here, right? This angle is called the angle of depression, because that's the angle from the horizontal that I'm looking downwards, right? So like down at you from, so you'll hear this sometimes in problems with like an airplane, right? People looking out of the airplane or a helicopter. And then this angle right here, the angle that you're looking up at me, that's called the angle of elevation, right? So it's from the horizontal and you looking up. And that one probably comes up a lot more in a lot of problems because we're at the ground and we're looking up at the top of a building or the top of a tree or something else. But notice that they are the same, right? So they're equal because since these horizontal lines are both horizontal, so they are parallel, these are actually alternate interior angles, right? So those are the equal. So the angle at which I look down towards you from a position higher than you are is the same angle at which you look up to me from that desk, right? So that's kind of the idea. Unless otherwise is specified, which will happen eventually, but unless we say otherwise, you can assume that buildings, right, and the buildings and the ground make 90-degree angles. You can assume that trees, right, oh, that's a terrible tree, that a tree and the ground make a 90-degree angle, right? You can assume that until we tell you otherwise, which won't really happen until chapter 6. Okay, so let's go ahead and do a little bit of practice without words. We're going to go ahead and solve for x. So the first thing I have to ask myself, okay, so step one, what do I know? And this is not just a trig word problem situation. This is anytime you approach anything. If you're trying to problem solve in math or in life, right, you should stop and think, okay, like what information do I have? Well, I have this angle 60. I have the side that is clearly opposite the 60 and the side that is touching the 60. What I clearly do not know is the hypotenuse. So I see the adjacent and the opposite, and my brain says, so what do I know, right? So I happen to know the opposite and the adjacent. The second question, and this is trig specific, is which trig function, right? So I know O, so the things I know are O and A, right? I know the opposite and the adjacent. So my brain says TOA. Now, could you technically use cotangent? Yes, but remember, we're going to probably be using a calculator to help us with this, and cotangent isn't a button in your calculator. So I'm going to say, cool, I'm going to set up a tangent equation, right? So I'm going to go ahead and set up an equation and say that the tangent of the angle I'm given, which is 60, right, equals the opposite over the adjacent. So I'm going to have to solve for x. Now remember, tangent of 60 is a number, so I'm going to multiply the x over. I'm going to get x times this number, which is tangent of 60, equals 32, right? And so I'm going to get that x is a 32 divided by the tangent of 60. Now, it's very likely, tangent of 60 degrees, keep in mind, it's very likely that my calculator is in radian mode because that's where it usually lives. So, yep, radian mode. So when I start doing things that have degrees, I need to make sure I switch over to degrees, quit out, and now I can go ahead and do 32 divided by tangent of 60. And I don't need to put the units in my calculator because my calculator knows what mode I'm in, and I get that this is 18.475. I didn't have units in the problem, so I don't invent units. If there had been units, if there had been feet or inches or something else, I would need to put that. And that's kind of the gist. All right, let's keep moving. All right, so you're going to do the same thing. You're going to solve for x, right? So again, ask yourself, what do you know, right? You have this 30-degree angle, right? You have the opposite side. You have the adjacent side. Now, interestingly enough, if you want, you could have used the 60, and if you use the 60, then which one's the opposite and which one's the adjacent are reversed, right? Same thing here. I know that this would be a 30-degree angle because 30 plus 90 plus 60 gives me the 180. So using the 30, though, I happen to know opposite and adjacent, so I'm going to go ahead and set up a tangent again, right? I'm going to do TOA. So tangent of 30 degrees equals the opposite over the adjacent, right? So I'm going to multiply the x over x, tangent of 30 degrees equals the 30. And remember, tangent of 30 is a number, so I can divide that over, and I get 30 divided by the tangent of 30 degrees, right? And in my calculator, I'm already in degree mode because I was already there last time. So 30 divided by tangent of 30. There's a lot of 30s in this problem. And I get that x is approximately 51.961 or 2. And again, no units in the problem. I don't have to invent units. All right, so we're going to go ahead and do a word problem now. So Pitts has to get the volleyballs that are stuck up against the windows in the gym, right? He pulls the giant, scary 30-foot ladder out and leans it up against the wall so that the angle of elevation is 75 degrees. To the nearest thousandth, how many feet up the wall does the ladder reach? So here we don't have a picture. So my first piece of advice is, in the last couple problems, I said you should figure out what you know. It's really hard to figure out what you know if you don't have a picture in a problem like this. So I would suggest you draw it. Nobody needs it to be drawn to scale. Nobody needs it to be pretty, but you're going to be better off if you draw it, okay? So I have this triangle, like there's a 30-foot ladder, and it's leaning on a slant, right? And that slant happens to be 75 degrees, not at all drawn to scale. We can assume that the ground and the wall make a 90-degree angle unless we're told otherwise. Pitts is standing at the base of the ladder ready to climb it and go get the volleyballs, right? That's Pitts. Except, like, he does not have stick figure arms. He could probably, like, I don't know, break my computer in half. Anyway, so we want to know how high this thing reaches up the wall, so I'm going to call that H. You could call it anything. I'm going to call it H. So now once I have a picture, I have to figure out what I know. Relative to the 75, I seem to know the opposite side and the hypotenuse, because the hypotenuse is always opposite the right angle, right? So I think, oh, hey, I need to use so, right? I'm going to use sine. So the sine of 75 degrees is going to be H over 30. If I multiply the 30 over, I can type in my calculator 30 sine of 75 degrees to get my H. So 30 sine of 75. I don't need the degrees in the calculator because I'm already in degree mode, and I'm going to get that H is approximately 28.977 or 978 feet. And here I do have units, so I need to make sure I have the units. And that's pretty far up because 75 is a pretty steep angle. So like this ladder actually looks more like pretty close to vertical. I'm not doing a great job drawing it, but it looks pretty close to vertical. It's reaching almost the full 30 feet up the wall. All right. P9, the flagpole outside the school casts a 14-foot shadow if the angle of elevation of the sun is 70 degrees. To the nearest thousandth of a foot, how tall is the flagpole? So again, I would suggest that you draw this. So I'm going to go ahead and put the sun on this side, okay, and I'm going to put my flagpole here. Okay, flagpole. Okay, so the way that shadows work, the sun hits the top of the pole, and again, not drawn to scale at all because I'm terrible at drawing things, but you get the gist. It doesn't ever have to be drawn to scale. Okay, so the angle of elevation of the sun, right? So this is the shadow, right? And I know it's a 14-foot shadow, right? The question is, how tall is the flagpole? I'm going to call that F. So the angle of elevation of the sun is 70 degrees. We have the same basic triangle that we just saw when we dealt with the Pitzner problem, except instead of knowing the hypotenuse, we seem to know the two sides. So when I list what I know, right, I seem to know I want the opposite side, right, and I know the adjacent side. So that means TOA. So my brain says, oh, wait a sec, TOA, right? So I want tangent of 70 degrees equals the opposite over the adjacent. So I'm going to type into my calculator 14 tangent of 70, and that's going to give me my flagpole height, right? So 14 tangent of 70, and I get that the flagpole is approximately 38.46, either 4 or 5, right, round or truncate, and it's feet, right? Again, if there are units, make sure you have units. You should assign a variable on your diagram. All right, cool. All right, so E10 is a really fun problem. It's called indirect measurement. So I give you this problem, I think on your review, I give you a problem about King Kong. Sometimes I give you a problem where this is City Hall. So indirect measurement is the idea of not being able to get close enough to actually measure something. So what's going to happen here, so you're in a car and you look up at the top of a mountain from really far away, 13 miles, okay? And the angle of elevation is 3.5 degrees. You then drive 13 miles closer and you look up again, and now the angle of elevation is 9 degrees, right? So the question is, can you find the height of the mountain? So you can, and the trick here is that you're going to have to assign some variables, and it's going to be a little bit complicated. But once you get the hang of it, these problems aren't awful. So let's make this little triangle the red triangle. Okay, I'm going to make this little one red, and it's a right triangle. Okay, and I'm gonna call the height of the mountain H. And then I'm going to have this big blue triangle, right? The big blue triangle goes the whole way out. right? And that also has the height of h. So basically what's happening here is there are two triangles. There's this long triangle that has a height of h here and an angle of 3.5. I should have switched to the skinny pen, my bad, right? And then there's the, sorry, it's very frustrating that it doesn't default to the skinny pen. Then there's the red triangle, which is smaller, right? But smaller in terms of this length, right? But it's also got a height of h, right? And I know that this is 9 degrees. And again, I'm just terrible at drawing things, but we'll survive. Okay, so I know that's 9 degrees. Here, I could do better. Close enough, okay. So h, and this is 9 degrees. Okay, so the trick here is that I really need to, I don't know anything about the two hypotenuse values. I do kind of know some stuff about these sides. So I don't know this measurement on the red triangle, so I'm gonna call this measurement x. And what that means is on the blue triangle, this side is the entire 13 plus x, right? So on the blue triangle, this is a 13 plus x, which is tricky. But basically what I'm looking at now is I'm looking at a triangle where for the blue triangle, I seem to know TOA, right? The opposite and the adjacent. And for the red triangle, I also seem to know TOA. So I'm essentially going to do two separate problems here. I'm going to set up a tangent equation for the blue triangle. I'm going to set up a tangent equation for the red triangle. And then I'm going to figure out how to use them together. Because I only have two variables. I have x and I have h. Two variables and two equations is solvable. So the tangent of 3.5 degrees should be the opposite, which is h, over the 13 plus x. I can solve this for h by multiplying the 13 plus x over, and I get that h is 13 plus x times the tangent of 3.5. In the red triangle, I can set up that the tangent of 9 degrees is h, the opposite, over x, my adjacent. So I could multiply the x over, and I can also solve for h and get that h is x tangent 9. H is the same as h, they're the same mountain, right? So since this h value is the same as this h value, I can set the red thing equal to the blue thing. So I can say that 13 plus x, the whole quantity, times tangent of 3.5 degrees has to equal the x tangent of 9 degrees. And now I'm going to be able to solve this for x. So I can solve for x, and then I can use x to find h. So this is a difficult problem. There's a lot of steps to this. You're going to see one of these on the test, and it's going to be the same basic problem, but the same number of steps. It's a lot of steps. So let's keep working our way down. So solving this for x is a little tricky. There are two x's in the problem. There's an x here, and there's an x here. I have to treat everything else in the problem as though it is just a number. So I'm going to go ahead and distribute and get that this is 13 tangent of 3.5. And you do need to keep it as tangent of 3.5 until later, because if you round anything early, then it has disastrous effects on your final answer. Like if you're going to be an engineer and you're designing bridges or planes, please don't round early. Please wait till the end, because it's going to have sort of a bad impact. So I now, remember, I'm solving for that x. Everybody else is just a number, right? So I'm solving for this x. So what I'm going to do is I'm going to take this whole thing and move it to the other side, right? So I'm going to get 13 tangent of 3.5 degrees equals x tangent of 9 degrees minus x tangent of 3.5 degrees. Now, so I see that I now have these two x's on the same side. So I can factor out their coefficients, right? I can say, hey, I can factor out the x essentially and just combine the coefficients. So I'm going to get 13 tangent of 3.5 degrees equals x times this ugly monstrosity. It is important to notice that you cannot combine these two tangents, okay? This is not the tangent of 5.5, okay? It's two separate numbers. So it's tangent of this thing minus tangent of this thing. So then I divide that over, and I get that x is 13 tangent of 3.5 degrees divided by the entire thing, tangent of 9 degrees minus tangent of 3.5 degrees. And I can type that in my calculator. Or, so I can type that in my calculator and get an approximate answer, but that's my x, right? Once I know that, the easier equation for h, the easier equation was the red one. So the easier equation for h, if you go back up here, was this one. H is just x tangent 9. H was x tangent 9. So I can basically plug in this entire thing for x, and I can type in that h is this whole thing, 13 tangent of 3.5 degrees divided by tangent of 9 degrees minus tangent of 3.5 degrees, all times the tangent of 9 degrees, and I can get a value for h. Now, you don't have to stop in the middle and get x. You could get a value. If you get an approximate x value, you need to store it as something, and then you would use that number here. You don't want to use a rounded value. So if I wanted to find x, I would put in 13 tangent of 3.5 parentheses closed, open the parentheses, sorry, divided, open the parentheses, tangent of 9, you got to close the tangent, minus tangent of 3.5, close the tangent, close the denominator, and then we go. So I get that this is an 8.178 ... but I'm going to store it as alpha a, and a is what I'm going to use. So now I'm going to do alpha a tangent of 9, and I'm going to get that h is approximately 1.295 miles. That's how tall the mountain is. All right, and it was in miles. We can go back and double check, but it was 13 miles. So not a short problem, right? But you're going to see this problem on the test for sure. So it's King Kong or Godzilla or City Hall, but you're going to see the problem on the test, right? It might be King Kong, like he's a monkey, and he's mad, and he's really tall, and he's like, rawr. That's my King Kong. He doesn't look very good. I get it. I shouldn't be allowed to draw anything. Rawr. He's got angry eyes, right? And he's, I don't know what a monkey's face looks like. I don't know. He kind of looks like an angry teddy bear. I'm sorry, everybody. Anyway, he's an angry teddy bear. This is supposed to be King Kong. So, or a really angry bear. It's unclear. Anyway, so you're going to see that problem. Okay, so let's walk through another one that's similar. This is also indirect measurement. So try it without me. The key here is, yet again, you're going to have two triangles. So notice that the key to this problem was that within the diagram, there were two right triangles. Notice that it was no use to me to look at this triangle, right? This triangle has no right angle. That's not to say that you can't use non-right triangles for things later. When we get to chapter 6, we're going to do a lot of stuff with non-right triangles. But at this stage of the game, you just don't know how to handle those non-right triangles. So you really have to look for the right triangles in the problem, okay? So an observer is 350 feet above sea level and sees two ships directly offshore. The angles of depression are 4 degrees and 6.5 degrees. How far apart are the ships? So one place to start, just to be clear, it's a really good idea to figure out what thing they're asking you for. And in this case, they're asking you for this measurement right here, right? Sorry, that kind of erased itself. So it's good to know what they want, right? That's helpful. So my argument is that there are two right triangles here, right? And there's two different ways to get this value, right? It is worth noting that the value I just highlighted there is also the same value up here, right? Like if you wanted to write the triangles upside down, like the distance of the two ships horizontally is the same, top or bottom, it doesn't matter. So, so when you're doing this, I'm going to argue that there are two triangles. There's this one, okay, so there's this triangle to the ship. I'm not doing a very good job drawing it, but there's this triangle, right? That's the big one, right? And then there's this triangle, which is the smaller triangle, right? So, so my argument is that you seem to want this measurement, like this is the measurement you seem to want, right? Which seems to me to be the distance, like it's the difference between the long leg of the red triangle and the long leg of the blue triangle, right? So if, for instance, I wanted to call this side, I would argue that you could call the entire red side, right? I could call this entire red side, let's say Y, right? And I could call this little blue side X. I would argue that the thing that they want, this green spot right here, I would argue, oops, sorry, wrong color. I would argue that the thing that they want seems to be the red side, right, the big side, minus the little x that I labeled, right? I would argue if you found, oops, wrong color. I would argue if you found y and you found x, you could just subtract them. So I think that what we want, based on the letters I labeled. So if you looked at this triangle, right, if you looked at this triangle, the blue triangle, and again, I drew it upside down. I mean, it doesn't matter how you want to draw it. I drew it this way. This height is a 350 everywhere. So that's a 350, right? And this is the thing I called x. I would argue that you can find x, right? And so this thing, right, this thing is a 4 degrees, right? And I called this y, and this is also a 350. So I'm going to argue that it's about finding x and finding y and then subtracting them. That's probably the easiest way to do this problem. So I look at what I know, right? We make that list again, and I notice that relative to the 6.5, this is the adjacent side, and this is the opposite side. So I'm using TOA again, right? Tangent of 6.5 degrees equals the opposite over the adjacent. So I'm going to argue that my x times tangent of 6.5 degrees equals 350. So my x is 350 divided by tangent of 6.5. And honestly, there's no real incentive for me to find what x is, because I'm going to use it in the end equation anyway. And I'm going to say that the same thing applies for tangent. Again, I know the adjacent side, and I know the opposite side, so I'm going to go with TOA, right? So tangent of 4 degrees equals the 350 over the y. So if I do the same skill, y equals tangent of 4 degrees, y times tangent of 4 degrees equals 350. So my y is going to be 350 divided by the tangent of 4 degrees, right? I'm going to argue that I just need to subtract these two values. So when I go up to find my answer, I'm going to argue that this is 350 divided by the tangent of 4 degrees minus 350 divided by the tangent of 6.5 degrees, right? So my answer is going to just be that value. And if you wanted to find the x and the y ahead of time, you certainly could, but I don't know that there's a huge incentive to do so, right? The goal here is just to find the answer, and I already know the relationship I need to find that answer. So it's the tangent of 6.5, and enter. All right, so I get that this is 1933.32, either 2 or 3, and it was measured in feet, right? So this is my answer. And I would probably, if I were doing this on a test, I'd probably delineate that this work was separate from the bottom stuff, that I used the bottom stuff to get there. All right, cool. So that's it for our word problems. We're going to talk about one other thing that's not a word problem. I just wanted to show you kind of a cool trick. So random cool trick, not a problem coming with this. I just think it's neat. So there's a cool trick for measuring the height of something tall with a mirror. So this is not actually trig. It's similar triangles, but it's just a really neat thing. So if you want to measure the height of a tall thing, so you get a mirror, right? You get a mirror, and you place it a set number of feet, whatever feet you think are reasonable, away from the tall thing. I picked 20 feet. The taller the thing is, the farther away you probably want to go. It depends. It's up to you. So I picked 20 feet, right? So I walk away, right? So I place the mirror 20 feet away, and then I walk until when I look back, my eyes look in the mirror and see the top of the thing, right? Like that's the top of the thing, right? So I walk back till I see that. So what I would then do is I would mark that spot, and I would measure this distance to be x feet, right? Because, so the way mirrors work, the angle at which the light comes in has to be the same as the angle at which it leaves. So since these are the same, and since the 90s are the same, what I have are two similar triangles. So essentially h, the height, has to be to 20 as the height of my eyeballs, because it's not actually my head we're measuring, right? It's my eyeballs. The height of my eyeballs would be to x. So essentially h is to 20 as the 5 is to the x, right? Meaning height of the thing is to the thing to the mirror, that distance, thing to the mirror, as the height of your eyes is u to the mirror. And you could solve that and figure out the height of something. So that's kind of cool. I mean, obviously it's not super exact because, for instance, if it's a building or something, you might only be seeing one edge of it. It might have other tiers that are taller, but like you get kind of the gist that if you it also, could depend. Subtle differences might mean that you're not super accurate, right? Like maybe you didn't measure quite how high it is to your eyeball, or what, but you get the idea. It's definitely within a pretty good margin of error that you can estimate the height of an object, which is kind of cool. All right, that's it for this video.